Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Suwei Wang and Lile Wang with us today. Hello, Suwei. Hello, Lile.
Hello, Frank. Hello, everyone.
Yes.
Very good. And where are you located at? What's your geolocation?
So, geologically, we're located in what's called the Kepler Institute of Astronomy and Astrophysics in Peking University.
Okay.
And I don't know whether it's a coincidence, but the road just outside the office is located exactly at the latitude of 40 degrees north.
Oh,
So,
really?
like on the line on a circle of latitude 40 degree north in
Cool.
Peking, in China. So anyway,
Very cool. I never knew that. Ah, right. Makes it easy to know where you're at. Very good.
right,
That's
exactly.
that. Well, that's what I get for asking a very literal question. What is your geolocation? You answered it correctly, so that was fantastic. That was great. Very good. Very good. Let's see. And Sui, what do you like to do for research?
Okay, recently I'm doing some programming works, especially some GPU programming for microlensing, just as the article I'm going to introduce. Yeah.
Yes, and
Cool. We'll get to that.
and so I probably forgot to introduce that he's actually now a PhD student,
Ah,
one of the
yeah.
PhD students in the Kepler Institute of Astronomy in the KIA in Peking University. And nominally, I am his PhD advisor.
Yeah.
The other co-author of this paper, Dong Subo,
Yeah.
he unfortunately he's unable to join us this morning because he's busy with his grant proposal. But he just want us to convey his warmest, I mean, saying hi to everyone of the audiences. And probably, unfortunately, he's not able to join, but we still want to, I mean, have the interview with only two of us.
Very
Please.
cool. Think that was a great shout out. Very good. Very good. And Lily, what do you like to do for research?
Yeah, so theoretically, I'm a person in planet formation. My PhD thesis was on polar planetary disks, and I also work on this even nowadays. My latest publications are all on polar planetary disks,
Okay,
plus atmospheres of exoplanets.
cool.
Plus, I also do a lot of GPU programming. That's how and mostly how I am involved in this project, developing with my student Suwei Wang to compose a GPU code so that we can utilize one of the most powerful kind of devices nowadays to deal with or to the prospective data that's going to be released in future
Okay.
that we can expect from
Yeah.
something like domain telescopes and so forth. Yeah, I also do a lot of GPU programming. I also develop my numerical simulation system on
Cool.
GPUs and use it to do literally everything.
Very cool. Very cool. Oh,
Thank
very
you.
yeah.
Yeah.
And that is going to bring us to this very awesome APJ supplement article.
Mhm.
It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
Yep.
Okay.
Wait.
Okay. Hello. Thanks
Oh,
for
take
for
take
your invitation.
go.
Yes, yes, please go ahead.
Okay. Before diving into the paper, I'd like to first provide some background knowledge about microlensing to help everyone better understand our work.
Hmm.
Okay. The so-called gravitational lensing is a phenomenon that the light comes from a background source is deflected by the gravity of a foreground source. Okay, like this.
Yep.
And the foreground source would act like a lens and create multiple distorted image of the background source.
Yes.
Yeah, and the microlensing is a specific kind of gravitational lensing. Unlike the strong lensing, which the multiple images could be resolved, in microlensing, we could only see the combined light of all of the images and form a characteristic light curve.
Yes.
Okay. Um,
I'm with you.
the typical background source for micro lensing is usually a star,
Hmm.
and the lens object is another star. Okay, with its planet, and when the exoplanet and its host star is moved relative to the background source,
Yes.
the apparent magnitude of the background source would change and form a characteristic light curve.
Yes.
And by fitting this light curve, we could we could extract some useful information about the lensing system.
Uh-huh.
For example, the physical parameter, the mass ratio, that is the mass of the planet divided by the mass of the sun, and mass of the star. Okay. And for example, their binary separation, or the distance between the two objects.
Major.
Yeah.
Mhm.
And during the last few decades, the microlensing method has been proved to be a successful method for detecting exoplanets. This method have already discovered for dozens of exoplanets.
Mhm.
And in our work, okay, back to the abstract, and uh, we develop a new GPU-based code called Twinkle, and this code is for binary lens. The lens object is only one star with one planet, and the method we use is counter integration method.
And by the way, the
Okay.
naming of this code, Twinkle, actually comes from Suwei himself. Twinkle,
Yeah.
twinkle, little star.
Yeah.
Sorry, I don't know who you are.
Yeah, I guess this song is world famous. Everyone know about this song.
Yes.
Besides,
Most anyway. Yeah.
yeah.
Mhm.
Besides, if time allowed, I should explain that this name is also an inside joke between me and my the girl I love. So finally, I choose this name. Okay, not so academic, but I love this name.
Go ahead.
Okay.
Oh, we're learning all kinds of things here today. Okay.
Finally, the Twinkle code, compared with the previous CPU-based code, it could give a significantly faster computational speed.
Mhm.
And with some algorithm improvement, it could also provide more reliable magnification results, especially for lower mass ratio.
Yeah.
That indicates actually the mass ratio between the planet to be detected and this whole star.
Yeah.
Which is important if we ever want to detect Earth-like planets using the microlensing technique.
Right.
Yeah.
No.
Okay.
Yes.
Okay. So that is the abstract. Then let's talk about the introduction.
Okay.
Here, since as I mentioned before, the microlensing is a gravitational lensing event. So in principle, we need to solve the geodesic equation. It's really complicated, but fortunately, for microlensing case, the equation could be simplified, especially for point source. For the point source approximation, the geodesic equation would reduce to a so-called lens equation. That is the equation 1. We will talk about it later.
Okay.
However, please wait. Still here. Sometimes the point source approximation is not valid because in some position, the point source would give out an infinite magnification. That's unphysical.
Points.
So
Right.
we need to consider the extend source effect.
Right.
Usually there are two approaches to solve this problem. One is called the reshooting method, and the other called counter integration method.
Mhm.
Yeah, here. And Twinkle uses the later one, the counter integration method. The basic idea is, okay, here is the extended source, and we will choose a series of point source along its edge or edge. Okay, edge along the edge of the source, and compute their image position. And connecting this image position, we could give an extended image.
Yes.
There's an important property that in microlensing, the surface brightness of the image and the source are conserved. Therefore, to get the magnification, we only need to dividing the area of the image by the area of the source. Okay, that's the basic idea, right? However, both the reshooting method and the counter integration method, they all need to take about hundreds to thousands of computational time longer than point source approximation.
Okay.
That makes it a big challenge for the subsequent fitting works, especially when we consider the future space-based microlensing project like the Roman Space Telescope. Their high sensitivity would provide more observed events and larger parameter space. Okay, this fact makes the fitting works the time consumed is really high. Okay.
Yes.
So to improve this situation, and we have noticed that the most time-consuming part in the content integration method is the to calculate the position of image for each sampling point source.
Right. Right.
And we find that this process is independent to each other and could be performed in parallel.
Mhm.
Yeah. So we consider to use the GPU. Yeah, it's an efficient device for parallel computation.
Right.
And finally, we could use this to give it a significant acceleration.
Cool.
Yeah.
Very nice.
Yes,
Mhm.
Command.
Okay, I'm with you.
Probably it's a better way for me to say about these kind of things slightly later, because that was located in the section 3 and 4 of this paper.
Mhm.
So we just have Suwei continue his introduction down to the equation 1, please.
Okay.
Yes, let's go to
Okay.
the lens equation.
Yeah, dive into all the mathematics
Yeah.
with these.
Yeah, I'm sorry for that. I just want to talk about this equation. Okay, only the equation 1,
Okay.
not so many mathematics. Okay, okay, let's see some algorithm details. Here the equation 1 is the so-called length equation. Here the zeta is the position of the source point,
Okay.
and the z is the position of the image position.
Okay.
And here the z1, z2, m1, m2 are the positions and masses of the length object. That is the host star and the exoplanet.
Reduced quantities, otherwise the dimensions are not consistent. Reduced to dimensionless quantities.
Yeah,
Yep.
yeah. All of the quantities is dimensionless. The size is normalized by the Einstein equation. That is
Not Einstein equation, Einstein radius.
sorry,
Einstein
radius.
radius.
Einstein radius.
Okay.
That is typical size or in microlensing case. Yeah.
Which is presented in equation 3. And that's a characteristic size of the lensing problem, and we normalize every single thing to that so that we are solving the things that in a dimensionless way. Go ahead.
Yeah. Okay. And here we will notice here in equation 1. The equation 1 also involves the conjugate of the
complex conjugates.
Yeah, the complex conjugate. Both the zeta and z are complex numbers.
Mm-hmm.
Here, the complex conjugate is non-analytic. So the usual approach is to transform the length equation into a polynomial equation.
Fixed order algebraic equations.
Yeah.
And unfortunately, according to one of the most famous French mathematician, Galois, the fixed order algebraic equation does not have analytic solutions.
Yes.
To solve it numerically.
Yeah.
And this is one of the emphasis of all lensing dealing numerical calculation methods.
Yeah.
And this is
yeah, right. And here we need to transfer this length equation into a fifth order polynomial equation. And we should emphasize that there is the first algorithm improvements we made. Here the polynomial equation.
Yes.
We optimize the way to generate the coefficients. Because what should I say?
Without this kind of improvements, we notice one thing that could affect the accuracy of the solution significantly. This thing is what's called a catastrophic subtraction or catastrophic cancellation in numerical calculations.
I'm with you. Yes, understood.
Yeah, it's a nightmare for almost every single person doing the numerical simulations plus data reduction processes. VBL, the VB binary lensing code, which is a great one, people have been using it for many years. It's performing pretty well in most of the parameter spaces. However, when we go down to, especially down to the places to lower mass ratio applied to star mass ratio, we notice that the catastrophic cancellation could cause problems, or even troubles from time to time.
Yeah.
And this will significantly slow down the calculation whatsoever, even if it doesn't lead to an inaccurate or incorrect result. So that is actually the first improvements we have ever made to the method before we ever implement it on the GPUs.
Yeah. Yeah, okay. And the result, the improved coefficients is shown in equation 6, not here. That is the traditional method.
Yes.
6. Yeah.
I'm getting there.
Right. And we can see that that is the improved one, and it has the better numerical performance, and it's easy to be applied to anyone's work.
Yeah.
Yeah.
So if anyone wants to implement this kind of improved method, it will be quite straightforward.
Yeah.
And the mathematics behind it is also kind of straightforward. We just do the analytic expansion and do the subtraction analytically to avoid numerical subtraction.
Cancellations. Yeah. Yes.
More accurate results could be generated.
Yeah, indeed.
Yes.
Yeah, and I'd like to show the figure 1 to give an illustration of the improvements in the coefficients.
Yeah, figure
Yeah,
one,
the
please.
figure 1.
Figure 1, please.
Figure 1. Let's slide down.
Yeah.
We're going to zoom out a little bit. Boom, boom.
Yeah, thanks. Okay, here we can see the difference of different coefficients generated method. Here we give out the cases. In this figure, we show the extended image. The green region is the extended image.
Okay.
And here there are some points, the blue point and pink point as the edges.
The edges.
The boundaries.
The margin of all these kind of
I still got it.
Please.
Okay. Here the colorful points is the point images. And here we can see that in the red box, the bottom panels is the zoom in of the red box.
Gotcha.
And, yeah. Here also we can see some gray points. We will explain it later.
Yes.
Yeah. And we can see that the conventional coefficient method face some problems in this case because of the numerical issues.
Yes.
The margin becomes irregular.
Yeah.
That's made great trouble for the subsequent steps.
Yeah, because we have to connect the points in order to get the geometry of the images. If we do not connect the points correctly, we do not get the accurate area of the images, and we get the ratio between the images and the source.
The magnification.
Magnification.
Right.
And it will cause troubles. However, with improved methods, as we can see in the lower right panel, everything regular, and the geometry. By the way, one thing that we probably want to emphasize is like the red dots here are the margins of what's called the real images, and the gray dots here are what's called the ghost images.
Yeah.
In theory, these boundaries of ghost images plus the what's called the real images should be perpendicular to each other near the intersections.
Okay.
Should be perpendicular to each other in intersections. However, if we do not do this kind of improvements, let's say a lower left panel here, you can see that everything here becomes irregular. It will be difficult to identify which image is which because they are irregular. Yes.
Yeah.
Go ahead.
Yeah, and we can see that with the improved and recursive coefficients, we can see the clear perpendicular condition and the smooth aligned boundary. So that is the improvement.
One of the new improvements that we have made.
Yeah.
And we can go ahead to our second improvement.
We also have some other two more other algorithm improvements. That is about how to detect the ghost image. Okay, that is in section 2, I guess 2.3, 2.4, 2.4, yeah.
2.4.
Yeah, right. The ghost image detector. So what is ghost image? Here, because in a binary lens microlensing system, one point source would produce 3 or 5 images. However, since the polynomial equation is a fifth order equation, it will always produce 5 rows.
Yes.
Right. So sometimes there would be 2 additional rows that don't satisfy the length equation. They are additional rows of the polynomial equation.
They are mathematically real for the polynomial equation, but they are physically unreal. So we have to include them before we really come into the calculation of magnification.
Gotcha. Very
okay. Yeah. So how to detect the ghost image? The basic idea is, okay, since it's not the solution of length equation, we just take it back to length equation and calculate the residual.
Right.
If it's the non-zero residual, that's a ghost image. Okay, that's a basic idea. However, the numerical error makes this problem more difficult.
Numerical error.
Sorry,
Numerical error.
numerical problem.
Okay. Okay.
Yeah, even it's a real physical image, it may still have a tiny but non-zero residual. For example, 10 to the minus 16 is still non-zero. So we produce some new method. The first one we called residual detectors. The name is a little bit misleading. The method is we mathematically prove that if there are two ghost image, then they have two residual. Both residual is a complex number. The two residuals, the sum of them should be zero. Should be zero.
Okay.
Yeah, so
Okay.
basically that's close to the relations between all these kind of algebraic roots of algebraic equations. It satisfies some conditions and we utilize it.
Yeah.
One of the very rough but not accurate analogies, like we all know that even for quadratic equation, we know the relation between these two roots. We
Right.
utilize similar things, although it's up to the fifth order. So
yeah, right. Yeah, that's the idea of how to prove it. And finally, we could check if the ghost image candidates satisfy this condition. If the residuals are the summation is close to zero enough. If so, we think okay, there are two ghost images.
Within the numerical tolerances, we identify okay, these are images.
Yeah.
So there's another way of identifying those images is to rely on their geometric properties.
Yeah, that is the second ghost image detector. We call it slope detector. Yeah, the 2.4.2. Yeah. The idea is just now we showed that there is a perpendicular phenomena in the ghost image and the real images.
Okay.
So we could check that whether this condition is satisfied. If not, maybe the classification is wrong. There is no perpendicular, so there is no real image to ghost image, the transition. Okay.
And this detector relies very sensitively on how are we generating or how and to what extent are we generating the roots near their intersections. And as we have already seen in figure 1, we have to deal with the solutions with sufficient accuracy before we apply this kind of slope detector to the ghost image detection this kind of missions.
Okay.
Yeah. Yeah, okay. So before is the 3 major algorithm improvements made by Twinkle. And with this, the help of them, we could give more reliable magnification results for lower mass ratio. The so-called lower mass ratio is mostly we test about 10 to the minus 6. That is the mass ratio about the Earth and the Sun. So that's why
that's why these kind of improvements could be important. Prospectively important in future missions that we all aim at. I mean, almost every single mission or exoplanet detection, especially include microlensing, emphasize we probably want to detect some aliens at some day.
Yeah.
Aliens on Earth-like planets, is likely.
Yeah.
So this is one of the prerequisites of detecting extraterrestrial life if you ever want to commercial our work in this way. Anyway,
there you go.
Yeah, that is the most of the algorithm details. And the next section, the section 3, is about the GPU implementation.
Yeah.
That section is how to fully leverage the potential of GPU device. That section I should give the
microphone to me. So I'll take over slightly. So I do a lot of GPU programming, and I realized that I do have something to do before we really implement on GPUs. One of the things is like we know that there are more than one manufacturers of GPUs nowadays. Yeah, we know NVIDIA are making the top tier GPUs, but we also know there are other kind of competitors on the market, including AMD plus Intel plus some other manufacturers throughout the world. One of the biggest issue that this kind of situation introduced to us is like this, let's call it the ecosystem of GPU programming is slightly scattered. We all know NVIDIA use there what's called CUDA. And AMD developed what's called HIP. HIP is close enough to CUDA, but there are still kind of subtle differences and nuances when we compare these two from one from each other. And Intel is making this story more complicated. They have their one API or OpenACC whatsoever. We did realize that in order to use our code across different kind of platforms, the best idea is to implement it on an abstraction layer. The abstraction layer will let us to, let's call it insulate all the implementations of algorithm we do on the mathematics side to the actual coding part of the that is facing the device and the programming models directly.
I'm with you.
Yep. And we do this kind of things. We are using one of the abstraction layer that I composed for another project. That's what I call a code called Kratos. I also submit a meta paper of this code to APJS and it's under review. So that's another story before we run into that. Well, oh wow, I'm advertising about another paper. But
no,
anyway,
that's perfectly fine. It's perfectly fine.
Okay. Thank you for understanding. And that tool is proved we have proved that the impact in terms of performance is minimal while extending or while maximizing the compatibility of the code or any code that's using that across all kind of platforms, and we take care. And it also introduced the capability of running this code on CPUs with one of the open source tool was called a heap CPU, developed by some people on the internet. We are available on GitHub, so that even if we all know that there's another way of implementing vectorized computation, what's called the many core system, probably proposed by ARM and some other standard maker or manufacturers saying that, okay, even if, let's say in 5 years, NVIDIA no longer make the top tier computing devices, and instead people are start to use many core processes. Okay, we're okay with it. We can also run it.
Okay. It's future-proof.
Yes. And in more detail, GPUs are this kind of devices. I will more like to willing to draw an analogy between a GPU and actually a cluster of conventional computing devices. Every single GPU has many computational units, what's called the stream multiprocessors, SM in short. Every single SM contains 16 or 32 computing units. Each of is close to or is similar to one of the cores in our nowadays CPU things. So one of the core tasks for us to implement on GPU is how do we coordinate these? Because the limitation of the GPU architecture within one stream multiprocessor, even if we have many different units that deal with float-point computation, we have to do the coordination because most of the computing unit at the same point of time has to execute the same instruction.
Okay.
We had better let all the units within one SM do the same thing at the same point of time. Now, it is admittedly nowadays with improvements of the GPUs, this kind of what's called a force synchronization is released because of the increase of the cache instruction cache. However, the better way is also is still to implement our computation methods in a kind of synchronized way. This is one of the challenges we face on the technical side. And the other challenge is the thing that we already explained, that is the scattering all the breakdown of the ecosystem due to the many different manufacturers. Each and every of them propose their own coding method, and we use the abstraction layer to stand for it.
Very good.
But there are also good news. The good news is like because the calculation of every single image in microlensing is kind of independent with each other, we can do the computation kind of in what's called embarrassingly parallelized way.
Right.
And the jobs can be distributed onto many devices with ease. And this is in clear contrast to numerical simulations, doing hydrodynamic IMHT simulations, because for numerical simulations, we have to deal with the communication job with care. Otherwise, communication can be the most costly part of all the computing processes.
Yes.
However, because microlensing problems are not suffering from these issues,
right.
can be done without too much trouble. That's why we do not have too many descriptions about how to deal with cross-node or cross-device communication.
It isn't there.
Yes, it isn't there in the
It
first
isn't
place.
there.
Right. So, and
Cool.
there is yet another thing. Well, it's very technical, a little bit tricky. It's like, so for some specific points, when we calculate the images,
Okay.
more iterations are needed
Sure.
for the specific points. If we just distribute all these kind of special points that need more iterations, it will hold up, it will occupy the stream multiprocessor and not releasing them to the other computation task.
Yeah, it's a load balance.
So we did a very special technique. We let all these points with extra numbers of iterations.
More iterations.
Yes, yeah, we want you to form a queue, and it stops at a fixed number of iterations and store all the points that need extra iterations and deal with the extra iterations concentratedly, so that this kind of occupation or unnecessary occupation on the GPU is kind of avoided in this way.
Yes.
And
okay.
let's come to the computational performances. We are going to talk about the improvements in performances from two different aspects. One, accuracy, two, speed. So
yeah,
good.
Yeah. Okay. After the really detailed talk about the GPU implementation, okay, I'd like to show two more most important figures. That is the figure 6 and the figure 7.
Let's go to figure 6.
Firstly is the figure 6. Yeah, here, this one. Here we produce a simulated light curve. The light curve both by our Twinkle and the previous CPU-based code. And here we can see that, the Twinkle could give all of the magnifications correctly and without the two spikes.
Correct and smooth. We will, unfortunately, at least in this specific case, produce two let's call it magnificent spikes. Two different cases. And that we do not really want. And we identify that these two spikes are the consequences of catastrophic cancellation during the procedures of generating the coefficients for the length equations to be solved.
And we can see that these two spikes is corresponding to the black circles in the right panel. And we can see that the boundary of the black circle is really close to the red caustic, the cusp of the caustic.
Caustics are the lines at which the communication is given. Yes. And when the circles and sources are tangent to the caustics, just causing trouble because all the mathematical system becomes quite singular. And we have to deal with it with key and this is just a very direct illustration of how our improvements in terms of coefficient generating is affecting the result and producing us a better accuracy.
That's the most important points.
Yes.
Because the position near the cusp has really severe numerical problems. So the previous code produced some spikes is reasonable. That is.
However, with improvements, we can avoid this kind of spikes.
By doing the analytic subtraction, take that part out.
Exactly.
I'm with you.
And so let's go forward to the figure 7.
Figure 7. Okay. Figure 7. Oops, sorry. Exploring parameter space. Mastery says figure 7 and performance and parameter space. Here we go.
That is for parameter space.
Okay.
In this figure, we're comparing the time consumption. Well, please be noted that the upper row are presented. The panels on the upper row are presented with logarithmic scales, so there's all logarithmic.
Yes.
Right. So they are presenting these two panels are presenting time consumption. So the bluer the better, the shorter the better, the smaller the better. Left panel with Twinkle. Right panel VBL. So we noticed that there's a feature. Well, we shouldn't call it a feature, a problem, a
Yeah.
white region to the lower left corner.
Yeah.
And this exactly where the accurate, yes, to the lower left corner on the, yes, here, exactly here. You see something white. Why is white? It is exactly where the inaccurate coefficient generation scheme is making us trouble.
Yeah. Yeah, not even the incorrect magnification. It still cost abnormally long time to give out to return the program boundary.
That's right. Right.
Yeah, near the boundary of the problematic region, we see, I mean, dark red, which indicates the time consumption is excessively long. That's where the system becomes quite singular due to numerical errors, numerical issues, and without proper improvements in terms of the coefficient producing, it's causing trouble in these regions.
And not to put too fine of a point on it, but this one is basically blue and this one is basically yellow.
Yeah, right.
And if we divide the left one with the right one, we get a ratio, and the ratio says us the general factor of improvements is a factor of about 100.
Yes.
Yeah.
That's the order of magnitude.
Yes.
One thing we have to concede or admit is like we are comparing one GPU versus one CPU cores. One CPU core. Nowadays, CPU have many cores. For example, on the typical server available nowadays, 128 cores per node is not a crazy number.
Right.
However, every single node server computing server or node, let's call it node using the terminology of high performance computing. Every single node can hold up to 8 GPU or even 10 something, sometimes 10 GPUs in total, 8 GPUs in total typical number. Yes. So we compare these two, the per node computing performance is still significantly better by using GPU compared to the conventional CPU version or CPU code like VVL. And this we can take care of another thing. It's like let's if we go back to the upper right corner, the problematic region is primarily located in the lower left corner, stands exactly on the parameter space that represents the mass ratio between the Earth and the Sun.
Yeah, that is 10 to the -6.
Yes.
In case that in the future we really want to detect some Earth-like planets with a lot with the data, incoming data with unprecedentedly high accuracy and sensitivity, we have to delve into the parameter space, the parameter subspace
down here.
Where the accurate production of the coefficient are important.
Yeah. Just in this figure, we have plotted some dots on this figure. That is a green squares and pink dots.
Yes.
Here, the green squares is the already known microlensing event that is observed by the ground-based microlensing projects. Yeah, and we can see that the green squares is really far away from the
problematic region.
Yeah, far away from region. So be relaxed. The previous result is always correct. Okay.
So we don't have to worry about the correctness of the existing result.
Yeah.
Sure.
But we can see that the pink dots is the simulated microlensing event observed.
They are the mock events.
Yeah. For the future space-based microlensing project, for example, it's just romance project. And we can see that the pink dots is really close to the left bottom region. So our improvement is necessary for the future larger parameter space observation. Yeah.
Very cool.
Yeah, that's
one of the expectations and one of the purposes, motivations of the whole paper, of the whole work, composing Twinkle with a better algorithm. So Suwei has already mentioned one of the future directions like that. So on the technical side, I do also have some expectations of the future works based on this. It's like for this moment, we rely on the double precision or FP64, 64 bits 4-point numbers, the capability of 64 to calculate the parameter or calculate the coefficients with care. However, we all know that GPUs nowadays, especially the consuming level GPUs like the RTX series or for NVIDIA RX series for AMD, They are
Yeah.
sold at a much cheaper price, lower by one order of magnitude compared to the what's called a computing or high performance computing GPUs.
Yes.
However, all these kind of consumer level GPUs emphasize their performance on FP32 or even FP16.
Yes.
So there are techniques that we can use to maximize the performance on consumer level GPUs by maximize the usage of FP32, the single precision 4 points.
Okay. Okay.
That we can still produce accurate results even by using FP32.
Yeah.
However, for this moment, we have not implemented on this current version of Twinkle. So this is our agenda, not now, but in the close future.
Yeah.
Another thing for this moment that we want to make our improvements is like, nowadays, every single person uses Python.
Yeah, right.
Mostly, the Twinkle code is programmed in C++, with a dialect like even the dialect like what's called let's call it CUDA-like or HIP-like
Yeah.
computing or programming style.
Mm-hmm.
It's not ultimately user-friendly if we ever use C++. Especially for when we want to integrate this with some other kind of modules or functionalities that exist on higher levels. For example, we want to do Markov chain Monte Carlo fitting, and
Yeah,
so
right.
you'll do it with Python. And another task for us to do is to develop an interface that encapsulates all these kind of details down to a Python interface so that people around the world can use it with ease.
Right.
Yeah.
Right. Very
It's
cool.
our future plans.
Yes.
Right. Very cool. Very cool.
Thank you. So that's probably concluding our introduction to the paper.
Yeah.
And Frank, do you have any questions?
I think it's absolutely beautiful work.
Thank you.
And I want to thank you for sharing that, and thank you for walking us through your very, very lovely article.
Thank you very much.
Very nice.
And we would also appreciate the opportunity for us to introduce our paper in front of all the audiences who are watching this video online.
Yeah, thanks for your support.
And I think maybe I do have a question. I guess you mentioned it, but I'm not. So is the code open source?
Yes.
It's on like a GitHub or something?
On GitHub, right?
Yeah.
Yes.
And the link is in the article?
Yeah, the link is in the article. Everyone
I
could
just missed
get
it. I just missed it. It's all good. It's all good. Well, cool. Well, Suwei, Lile, thank you so much for walking us through your very lovely article.
Thank you again.
Yeah, thank you.
Yeah, and that will do, everyone. And I hope this made your Twinkle Astronomy Day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.